talk to us today, and really appreciate Joe making the connection so that we could jointly sponsor this seminar between Civil and Environmental Engineering and Cereo, the Center for Environmental Research, Education, and Outreach. Steve, I have actually known, I guess, for a while, although we have only seen each other, I think, once since I was an undergraduate in his class at University of Kansas. So it's a special pleasure for me to be able to interact with him while he's here today. So just to give you a little bit of background, maybe some of you might be surprised at what a long academic career he had before going over to a very high-impact job in the nonprofit sector. He did his undergrad at Vassar and then did his graduate degrees at Yale. He held some prestigious fellowships before going on to a faculty position at University of Kansas, which is where I was in his classes. And then went on to Brown, and from there, the Environmental Defense Fund, where he is chief scientist. And along the way, he's gathered many laurels, including being on IPCC 2007, which means that we are in the presence of a Nobel Peace Prize awardee.
I've got 1,000 thumbs. I keep it in my pocket. Well done.
And now his role is to ensure that EDF's advocacy is based on the best available science. And so I think we're all really looking forward to hearing this seminar. Take it away, Steve.
Great. Thanks so much, Stephanie. I appreciate it. And so it's really great fun for me to be here because of the connections. I'll date Joe because he was my college roommate. And Brian and I have been working together on a big project that I'll talk some about here. I don't see Kent, but Kent Kellers and I have done research at Hubbard Brooks. So there's all these connections that just come together, so it's great fun. And I want to do it, I want to make this as Socratic as I can and as open to questions and dialogue, because I don't quite know what my audience and where you want to go, so you get to steer. And those of you know I have no lack of ability to talk and address issues, so we'll take it where you need to go, where it'll help you. And it's really about how can we integrate good science to affect good policy in a timely way so that we really do make it work. Because one of the things I would assert as a scientist who was an academic for 25 years, we're incredibly ineffective. And I say that about myself. So I thought I was one of those scientists who was actually pretty well connected in making my science relevant for the world and the decisions it's making, and I think I was pretty ineffective. Maybe a little bit more than some of my colleagues. So I think there's an alternative models, and Brian and I were talking about it earlier. I think there's some really alternative models we're trying to develop for how we bring science effectively to the policy arena in a way that is not anywhere secondary. It doesn't require scientists to advocate for things they don't know about. You need to be an advocate for your science or advocate for those things you know about, but you're still an advocate. I had lots of debates with folks about, I don't want to be an advocate, I got to stay neutral. No, you're not. If you're neutral, then you're not doing your job, whatever it is, because you think you have an insight about something. And you want to take that insight and apply it effectively to making sure that society can do a better job of whatever its goals are. And so I'm going to encourage you to become more of an advocate and to think more strategically about how you can bring whatever it is you're working on, whether you're a student or a faculty member, to affect policy that will bring greater benefit to society. See if I can use. So I'm going to talk about methane because it's what I do a lot of right now. And I knew nothing about methane essentially 5 years ago. I didn't work on methane. I'm a biogeochemist. I work on nitrogen and carbon. While methane has carbon in it, I never worked on methane. And, but it became clear to me as I thought about it that we didn't have good data about methane and its impacts on the climate, and that the climate conversation about the relative role among greenhouse gases was not well based on science. Not that the science was wrong, it's just we weren't maximizing the benefits. So when we think about methane and its impacts on the climate, if we put a molecule, or I shouldn't say a molecule, by weight of methane and CO2, the methane is 120 times more impactful relative to net radiative forcing when it's emitted. So that's the instantaneous. So we have to think about it differently than CO2. But the complicating factor is that if this is the proportion of methane or CO2 that's from when it's emitted, so 1, that when we emit it, and we look over time how much is left in the atmosphere, they break down at different rates. CO2 basically doesn't break down. It's absorbed by the oceans and the terrestrial biosphere, and then basically keeps on going for centuries. So once it gets up there, it's pretty much up there for a heck of a long time. Versus methane, which oxidizes, becomes CO2, breaks down relatively quickly. So we call methane a short-lived climate pollutant and CO2 a long-lived climate pollutant. And what became clear as I started investigating it, our relationship between these two groups of pollutants was not well worked out. And we weren't thinking about it strategically from a climate standpoint. And methane's important from a climate standpoint. This is just, if we look on the right, 100-year impact, sort of what's going to drive climate change based on a 100-year time frame. And you see the methane, the short-lived, which is those two boxes, the short-lived climate pollutants represent an important component of overall climate change drivers. But on the short term, on a global basis, they represent a much bigger proportion. So that if we care about the rate of warming over the next 30 years, I can have more influence on that by worrying about these than I can worrying about CO2 or the other long-lived pollutants. Now, if I care about what's going to happen to my daughter's grandkids, I should worry about CO2. And I'll come back to this in a moment. So time matters. EDF got involved in this after I'd been thinking about it some, because I did a presentation to our senior leadership after we were very heavily invested in the bill that failed in the Senate for climate. We were probably the organization with the most resources involved in trying to get that bill passed. And when it failed, we, as you always do when something didn't work, you sort of huddle and you sort of think about what's next. Sorry about that. And one of the things that I said to everyone in the room as we were doing that is it's all about time, time, time. What did I mean about that is that we hadn't effectively dealt with the fact that not all greenhouse gases were created equal, and that the solution for tomorrow isn't the same one as it is for 100 years from now. So we could start thinking about the problem in a more nuanced way. So we did an analysis. We realized the underlying science wasn't very effective in that. So we developed something basically called the technology warming potential. So we could begin to look at what's the impacts of moving from fuels, moving from coal to gas, from diesel to gas in a vehicle, or gasoline to gas, and was one or the other better for the climate? Because unless we could answer that, and over what period of time? And I won't get into details of that. I think the last time I was here I actually talked about that. But we could convert that sort of framing into how much methane could be leaking from the natural gas supply chain and ensure that there was a net benefit to the climate at all points in time. So if you look at this graph, this is years until climate benefits versus the percentage of the natural gas in the supply chain that leaks at some point across the supply chain. So if you're going to convert a coal plant to a natural gas plant, you want to get climate benefits, you need to make sure that your emissions are below 2.7% to get those benefits starting on day one. If you say, well, I don't really care for the first 40 years, the emissions rate could be 4%. So this gave us a frame to understand methane emissions and its impacts and how it affects fuel switching. This was framing, all of this is completely consistent with all the science that had gone before, but it reframed it into a way that was directly applicable to policy. This got a lot of play in the policy community in addition to the science community. We weren't bringing in we weren't contesting the science, we were reframing the science. What mattered? Because we were having a big debate in our country, how much should we be using natural gas for vehicles? And if you looked at the time, it would have said converting from a gasoline car to natural gas was good for the climate. The only trouble was it was negative for 85 years, and it became positive in year 85, so year 100 it was better. But I'm not personally, now that was based on existing leak rates, and so maybe if we get the leak rate down, that would be different. But assuming the leak rate that was then thought to be present, I wouldn't say I'm willing to accept 85 years of damage to the climate to get a benefit in year 86. So we can think about this problem in that way. This comes together in what I refer to as the and proposition. This is from a paper by Shoemaker et al. In December of last year. To try to, and I won't go through this, it was in Science, it's a policy forum. It was called What Role for Short-Lived Climate Pollutants in Mitigation Policy. The bottom line is here, what you can think about is how do we maximize the climate benefits of policy? And what it basically says is unless you do both short-lived forces and long-lived forces, you won't see that benefit. Short-lived forces are determining the rate of change in the short term. That's this line if we just do it here. And these are a set of scenarios I won't get into. You can look at the paper. But so if we want to slow the rate of climate change right now, we can do short-lived forces. But once we clean them up, then they're not going to have much impact because we've already reduced them. If we do CO2 mitigation, well, it's not going to help us a lot in the short term, but boy, it'll make it a lot better in the future. So if we care about climate change, we got to do both. The and proposition. The scientific community spent a lot of time arguing about what I call the or proposition. It was as if they were, I can only do one. And there were some who said, well, we got to focus on CO2. But if in the immediate term, we've got to focus on the short-lived. To my mind, that was the wrong conversation. And so we have pushed really hard in a policy frame to make this about the and proposition. We're currently working on a reframing of global warming potentials in a way that will make that clearer, because one of the things we have not done a good job on is to socialize this concept, to actually get the broader community. And so we are trying, there's a group of us who are now working on a set of science papers to try and reframe this in a way that would actually allow folks to get their hands around it and more effectively understand the policy implications of this. Because this, while we have used this paper very effectively in Washington to get people to understand it, it's still pretty wonky stuff. And wonky stuff doesn't tend to get into policy. Joe?
So I think this is really helpful to us in thinking about what these policies required mean, and as you say, the coupling of them. But it's all here rendered in future temperature change or temperature change at a point in time. So is there anything that we could reframe the vertical axis in either regionally or globally to say something about, I mean, a half-degree shift or increase from 2 to 2.5 is not necessarily the same as 3 to 3.5. So
sure, and the impacts, ultimately we care about impacts, and that's some of what we can work on and what the IPCC does. Absolutely, you want to turn it into impact. So you're absolutely right. So one of the things we talk about is, well, what are the implications of slowing the rate of climate change? We just did a science day at EEF where we brought a lot of experts in talking about species migrations and disruptions of ecosystem. Boy, this makes a big difference. That gap, if we can slow the rate, will the systems and social systems, talking about coastal zone issues, will be much more feasible to adapt to it if we can slow the rate. We can populate that with a set of examples. And most people would argue that if we're even at this projection here that puts us over 2 degrees, the amount of disruption will be so great that we'll be cooked. We could use a more colorful word, but I won't. But anything up there is just completely disruptive. And again, when we think about the policy, it's how do you tell the narrative that's most effective with your audience? In some cases, it'll be what happens to our generation, me and my daughter. For others, it'll be what happens to our grandchildren. And the key is it's both. It doesn't matter. We don't have to pick. We shouldn't pick. And we've not maximized the climate benefits because we've been picking between these two. So this is the context. This is what gets me going in the morning, is figuring out how we can bring science to this conversation and ensure that we're doing as much as we can. I'd say we've been quite successful, and I say that with humility, but we've gotten the president already a year ago this summer, got up and said, we got to deal with methane. It wasn't on anyone's radar 2 years prior. It started with musing about all this stuff. We got the president to say it this past summer. We've got a methane policy coming. We've got the EPA talking about regulating methane for the first time from the oil and gas industry. Colorado passed regulations that requires regular maintenance and reduction of emissions from their oil and gas industry. We're putting it on the radar, but it isn't a substitute for 111D, the power plant rules. We've got to reduce the emissions of CO2 for the power plants. We've got to do both. Now I want to transition a bit to talking about how do we get to this place. So that's sort of the overview of the issues that we've been working on, what motivates me. But the key has been, before we could do all that, we had to acquire the data. And Brian can talk, I'm sure, go on for a long time, because he's been an integral part of this, working with us. And then understand the case of methane. I should have context. So EDF's approach relative to reducing methane emissions from the oil and gas industry. How do we bring those emissions down so we can maximize the benefits of any fuel switching to natural gas and ensure that we aren't doing any, getting any excess methane in the atmosphere that we could possibly prevent. So first is getting the data. We didn't know. The paper we published in PNAS, the Proceedings of the National Academy of Science, with some of this stuff that I just showed you, was, I forgot the exact title, was basically, we got to acquire more data. We had so little data, I called it, and was quoted as called it, it was a he said, she said, they said, we said problem. Everybody had their opinion, and nobody could prove the other person wrong. That's a hopeless, we'll never get good policy out of that. First, unlikely you get any policy, because someone says, it's not worth it, because everybody who comes in tells me a different story. And two, we didn't actually know what was the right answer from a scientific standpoint. So first thing we had to do was acquire the data. Then we had to understand where the leaks are so that we could then develop effective regulations to minimize those leaks. And we've been working our way down this list over 2 years. So one of the things that we do quite differently than we traditionally do in science is I want to do this whole thing in 3 or 4 years, from start to finish, because that's what's required to solve this problem. Not a 3-year science grant followed by another 3-year science grant, followed by 5 publications and another grant. We're going to do all of this short period of time, push aggressively. And it's to deal with, we've got a revolution going on in the unconventional gas. It's highly contested. You know, there are many people who think this is a very bad thing. Well, we need to get the rules right at a minimum. And we need to minimize the greenhouse gas emissions. If we could go straight to, we avoid this whole natural gas phase and go straight to renewables, I'm all with it. But until someone can show me the roadmap, I think we've got to focus on getting the rules right and, again, getting renewables as quickly adopted as possible. Then again, we can maximize the societal benefit and minimize the damages. So we developed a large study, a series of basic modules from production. Think of this as the natural gas supply chain, producing the gas, gathering and processing, transmitting the gas and storing it, and then the local distribution, which was actually, that project was housed here at WSU, and Brian was the lead on it. And then we had one end use because it was so much in the public arena, which was how much gas is coming from natural gas fueled vehicles, both liquefied natural gas as well as compressed natural gas. So we set these projects up. We set them up with multiple partners, so there are companies involved in doing this work, as well as they're all led by academics. We didn't wait for federal funding. We went out and raised half the money. EDF did, more than half the money from private sources. We take no corporate money. And then we went to academics and said, well, we want you, and Brian can tell me if this is not true, if his experience, but we went and we said, look, we want the best science. You're going to do it independently, but we want it quickly. And if it's going to take a long time, we're not interested. But and we're going to help define the questions so they're policy relevant. But their papers will come out all in peer-reviewed journals. So the rules of how we did it, led by academic research, deploy multiple methods. So, you know, because we weren't sure what the right answers were, we didn't say we know the right way to measure it, so we'll measure it as many ways as we possibly can in each of the segments. We'll have external peer review. We have people coming in and critiquing the work while it's going on, who are experts. We're going to release everything through peer-reviewed journals and make all the data available. These were a fundamental sort of framing for this project. Very different. This is led by an NGO. And it's all motivated by how do we get the right policies in place, not prejudging what they are. Say we want the data to drive. And what's been amazing to me is as we did this, we have lots of corporate partners. The range of the conversation is that everyone got to see the data. Things got closer together. So rather than arguing more, we argued less. Because you'd say, well, those are the data. What are we going to argue? I don't have, it's not the way I think the world's working. I'm wrong because I don't have an alternative explanation. So I'm just going to talk briefly because I really do want to make it a conversation. This is just the first study that was released. We've got a whole series, including one that Brian's first author on, well, several he's first author on that'll be coming out. This paper appeared a year ago. Dave Allen, who's a senior faculty member at the University of Texas, was the lead author. He did more than 50 briefings, not just in the United States on these results, across Europe. There were hundreds of press articles, briefings at the highest levels of Washington in every major department. So this is science he had never done, and he's the chair of the Science Advisory Board of the EPA. So I mean, he's done a lot of policy relevant. He'd never done science, in his words, you know, that had gotten this much attention before. So measuring gas, here's just kind of how long you have to go. So measuring gas out of these tanks, they have to tent it all. This is all just temporary piping. And I'm sure, Brian, you have similar kinds of pictures of your system. I need to get some from you. You know, of setting all this up so we can measure, making measurements that have never, ever been made before. So the kinds of results we do it across the country. The other thing that happens is people make measurements in one place and then sort of, well, we can't generalize, but still do it. So we wanted to make sure we're doing it across the United States because we cared about, you know, it's not about where's the highest place, where's the lowest place, but what's going on across the country. Just some quick results just to give you the kinds of things. This is, on this side is the EPA emissions reported by EPA from a particular source. And then what was found in that study. So completions were a large source in the EPA's estimate. And there are almost none here. Why did that happen? And this was really interesting because the response to this paper took a couple different forms. Some on Capitol Hill said, proof we don't need regulations. When in fact, the reason this happened is there's an EPA regulation that was taking effect while they were doing these measurements that required what's called reduced emission completions, which meant they had to capture this gas and either flare it or send it to sales. And starting the beginning of next year, they can't flare it, they have to send it to sales. You have to do something. You have to hold it or put it in a pipe or something like that. So what my take, and I think it's a pretty neutral take, is what this demonstrated is the regulations were very effective. Basically, what had been a source of emissions was no longer a source of emissions because these regulations were in place and these companies were adopting it. Now, we got access to these sites because we worked with 9 companies responsible for drilling half the wells, natural gas wells in the United States. So it was a coalition of the willing, and we don't have good data on the other half because we don't get access. You can't just walk up to a well. It's private property. There's also safety issues. So even if we could, you know, we're willing to jump the fence, it would be unsafe to do so. We don't know what's going on there. It would be both illegal and certainly unsafe. So I would certainly not want to send any researcher to do it. Yeah?
Did you suspect the other half are less compliant, and that's why they didn't volunteer?
That's an interesting, I don't think that's the reason, only because I do believe that very few of them, if any, have any data. So they don't know how compliant they are. And I won't begin to speculate on motivation, on why they were or they weren't. Some would also be, there is an opportunity cost. It takes money. It takes both money. So we did charge. These companies had to pay to the University of Texas a contribution to the study. And also it took people power, right? There were men and women on their staff who had to be going to meetings. When they go to their sites, there needs somebody there to, just for safety reasons, to make sure everything's going well. So there are certain opportunity costs that certainly for some companies I'm sure was an issue. I don't think that was the sole issue. And I'll talk about it in a second because of multiple methods. I'll come back to that. It's a great question. Just a few things. Pumps and pneumatics were much higher. So these are the valves that open and close and pump things around, and that was twice as high as what they had projected. Leaks from equipment was not quite double the rate. And then these are just some estimates. There's actually an additional one now that didn't add to the slide of these emissions from different, these are EPA emissions. That's what was found in the study. You see EPA going up and down. It's not because the actual measurements went up and down, because when you have a relatively limited data set, your assumptions become key on how many something happens or what your emissions are. And so they kept readjusting as they learn more, the emissions. And that's partially what these studies would allow, is to be able to do a better job of that. So we have to think again about this whole supply chain and all the studies. So there's a whole series. These are just reporting the ones that have been reported. We're going to double or triple the number here over the course of the next 6 months as all these studies come out. But we go across the supply chain. What's the estimated leak rates? And the part that will be coming out from here, we'll include it in this piece here. But we also talked about multiple methods. And I'll come back to that in a second. So that's just the way we're thinking about it. Nobody had done this. And there were estimates. There was a study, a report to the Secretary of Energy, but right before we began this, that estimated coming up with better estimates would take $100 million. And we should, by the time we're said and done, we'll have done all these studies, including Washington State University made a contribution. I don't know that they would think of it that way, but we restricted the amount of indirect cost recovery they could have, so we'll count that, right? And as well as the money we put in directly, as well as the companies, the whole thing will be something around $20 million that will have been spent on these studies. And we believe that we will have a much, much better estimate across the supply chain. But then one of the issues is these multiple methods. So one of the things we do is we also commissioned airplanes to fly over production fields and compare to what the University of Texas came up. And what do you think those emissions were relative to what University of Texas? Higher, lower, same? None of you saw anything in the papers? There's been some stuff in the papers about this. They were higher. So you fly over and you look at the total amount of methane coming out, it was higher than when you do the bottom. Well, what happens is one's what we refer to bottom up, and the other is what we refer to top down. When you count things, what happens? You're inherently conservative. If you wanted to count the number of chairs on campus, all right, you'd go around, and if you did it literally by counting, you'd miss some things. There'd be some chairs, you'd miss the classroom, whatever. So it would be a conservative estimate. But if we did it by some kind of looking down from the sky, and then we're going to make some approximations, and then we're going to subtract things that don't belong there, it's going to be a higher estimate. We have to, because maybe we didn't subtract all the right things. So there's this, historically in the literature, and a lot of it coming out of these studies that we've sponsored, is this discrepancy between the top down and the bottom up. And of course, the people who think that we should oppose gas point to the top down and say, see, look at all this methane leakage. It's a terrible problem. And people who think, oh, it's a good thing, say, look at the bottom up. It's a good thing. And so we realized that we had to, as a scientific community, and in order to get the policy right, we had to understand this difference. So we got 10 teams together, including folks from here, to work in a 2-week window in the Barnett in Texas, everyone coming together, bringing their methodologies. At one point, we had 4 planes in the air. We had lots of cars driving around. This was some work funded by the Sloan Foundation. And we are in the process of assembling those estimates for the first time, done in one place by all the methods, so we can understand these differences. And I won't say, because we don't talk about results until they're released, but I just say I think we're going to have a more satisfying answer at the end of the day than we had before. So this is this is an NGO-led effort. We're doing science in a different way and on a different timeline. So from the time when we applied to that money and the papers will get published, will be 15 months, maybe 16, 17 months. So we're going to compress it because this is critically important. We didn't have time to wait for the federal grant cycle, which would have taken in and of itself a year. And we care about something else which we refer to as the fat tail. The question is how much of these emissions, the differences between this top down and the bottom out, is having a few big emitters. The fat tail is an economic term for, you got this tail of distribution that keeps going out. Well, how important is that? That's a hard thing to measure because there aren't many of them, And if you only see it every now and then, you have to sample lots to find them. So if you look, these are distributions. This is the total emissions of methane coming from numbers of sites visited from these production sites. If you look at it, you see that you can get a 60% reduction in emissions from 10 to 20% of the sites. So if we could fix the leaks on a small percentage of the sites, we could get a big reduction. So that's a good news because it says you don't have to do everything to everywhere to see the benefit. And not only that, look at this side. Zero emissions measured from 10, 20, effectively 30%. 1/3 of the sites essentially aren't emitting much of anything. So we know how to do it right, and a few places are accounting for a lot of the emissions. That tells you this is a really solvable problem. And we commissioned a study by the I'm now spacing, sorry, the firm, but that developed this, what is usually called a McKinsey curve of this is, the axis is cost here, and basically negative cost, meaning you make money, and versus the total amount of avoided emissions. So anything that's green and below, you can do it at effectively no cost. And obviously, the big bars at the end are at very high cost. And so what it says is there's lots of emissions in this system that and this is only restricted to the things we know how to do. So this is not trying to fix something that we don't, magic. Is that there's lots of emissions that can be reduced and lots of emissions at no cost or at small cost, 40 to 50%, using existing technology based on existing knowledge. So there's a big answer. And that's, that's a critically important component. So there are solutions that can be deployed effectively to reduce the emissions that we're seeing. So that's the studies. That's ongoing. We'll have finished publishing those in the next 6 months. We think that we will have, I like to use the analogy of the elephant. Many people, blind people, trying to describe the elephant. I think we had no description of the elephant, or a minimal description. We'll now know the shape and the size of the elephant. What we won't have is some of the details. But how do we actually get this to happen on the ground in a way that works for companies? So if we go to the well pad, we decided to enter into a different parallel project, which we call the Methane Detectors Challenge. And I use the analogy as if we sit in this room and an alarm goes off, it might be sensing smoke. It might be sensing, I would assume in this room we have a carbon monoxide sensor or somewhere in the building. But we do in our home. So why can't we do the same thing for methane? Every well pad in America has the equivalent of a carbon monoxide sensor that when there's excess methane, it sends a signal back to headquarters, you got a problem. Go fix it. They work really effectively to reduce carbon monoxide deaths in our houses. Because it doesn't tell you where the problem is, it just tells you got a problem. But what happens to that detector if it goes off all the time and you can't find any problems?
Take the battery out.
Absolutely. You disconnect it because you get annoyed. It went off again. There's nothing wrong. So you have to develop a sensor that you can trust that doesn't have false positives, but at the same time works pretty well. Well, so we reached out to the community. There are a lot of new sensors coming out, and we reached out to the companies. These are our partners in this, and said, we think that the technology exists, but the entrepreneurs don't know there's a market for this. So we want you to step up with us and say, you'll buy it if you can produce it. So we reached out, did an RFP. We got 20 companies or entrepreneurs, some from academia, who said, we think we can develop such a system. We selected 5, and we said we'll give you, the whole idea was we'll give them free testing. So we don't give them money, but we're going to test their sensors with a neutral laboratory. They get access to a common site. If they pass those, they were taken out in the field of a production company where they get tested again. All the data comes back to the company. And then if they pass that, now they've got a marketable product willing to buy some and test. So we're trying to create the market for the next generation of sensors to see the reality of reducing these emissions. We needed to catalyze doing that. We have a target price of $1,000 overall that you can make. It makes sense if you could put, and there are 500,000+ natural gas wells in the United States. So put one of these sensors on every one of them. We're saying in the interim price of about $5,000 a sensor. So this is a way. The deadline was for the original RFP of the 20. They're now in testing. Literally this week, there's being tested, these sensors. And we'll see if it works. There is a challenge of a different sort going on at ARPA-E that's part of the Department of Energy. Advanced Research something agency. I always forget. It comes from DARPA Defense, but it's Advanced Research Product Agency or Analysis or something, Energy. So it's a part of the Department of Energy. I apologize, I can't remember what the acronym stands for. And they have another sensor challenge, but they're looking over the horizon. How can we even do them really good? Sort of get rid of the problem because we could sense anything. So they have a $30 million project they're running right now with a series. They'll pay researchers at different universities to develop these sensors and see, but that's going to take many years. We're impatient for that, so that's why we got our sensors. We want them out in the field in a year or thereabouts. So we want to try to use the market to affect change, find effective monitoring networks, get faster leak repair, and get the co-benefits the industry and the public and the environment can generate. We think we can do that by catalyzing the marketplace in this regard. Data, science, and getting the market to work towards that. Another partnership that we announced in mid-July an effort I've led, which was with Google. We wanted to map the methane leaks in the streets of the United States, which is what was the kind of work that was going on, parallel work that was going on here at WSU. So it took 2 years to develop the science. I told everyone we could do it in 6 months, but I got it wrong. So we have had 3 of these cars driving around the United States with methane sensors because, again, we take no corporate money. Google pays for the cars, the drivers, the sensors. We do all the data analysis and the science, and we raise the funds to do that. And we launched in July this partnership, and I'll just describe the sort of problem that we're trying to solve. So this is just the kind of data you get. You drive around and you get methane levels and you get this nice messy data. How do we turn that into leak maps? And Brian can explain it probably better than I can. And then you get concentrations. If you're driving and these are samples you're taking as you're driving along, you get these kind of maps and we got to turn that and you see here's the scale. These are different levels of concentrations and we're trying to turn it into, well, where's the leak in this? And how will we use that? Now if you wanted to know where the leaks are in the streets of any city in America before we publish this, you would have only one place you could go. Some BU published some maps for Boston, and Duke University published some for Washington, D.C., but they only had methane concentration. So it told you the location, roughly, and it said it was X parts per million. Well, anybody know what to do with these numbers? I don't. Other than that's higher than that. You know, there's more there and less there. What does it mean? So we wanted to turn maps into something that we could actually use to affect policy change. So we wanted to actually calculate the flux rate. But it's a complex world out there. So this is just, so this work, this is a German bus, because that's where Joe von Fischer, who's been working with us from Colorado State, was on sabbatical when he put this together. So he went out and took a picture of a German compressed natural gas bus, but this is actually data from Fort Collins. If you follow a natural gas bus around, you have elevated levels. We don't want to tell the utility, you're messing up, you got lots of leaks. It's the natural gas bus. So in this case, we couldn't tell you where the leaks are in this street because we can't sort out. It's thermogenic gas, but we needed to know that so we could get the policy right. So we knew we didn't know the answer there. I won't go into details because I do want to go to questions. So we had to develop a system. We're using, this is the trace of the gas, and we had to turn it into basically an integrated measure, which we call parts per million meters, that Joe developed that would allow us to then get a rough estimate to bin the concentration. We didn't care about the maximum. We care about the sort of overall area, the total quantity of gas sensed in the street using, and then we could test it using controlled releases. This is just the car that Joe used on an abandoned airfield in Fort Collins. And this is obviously not methane, but smoke coming out just to give you a sense of what you could do. So you create these artificial leaks and you put them in different places and you drive through them. and you can start to begin to understand how it maps. We ran all these with our Google car as well and developed this system of known methane leaks versus predicted. So you build a model, and the goal from the beginning that I gave to Joe is I just simply want to know, is it a low leak, a medium leak, or a high leak? Because the concept is, if I can tell the utilities where most of the gas is coming from, they can focus their energies on repairing those places. What they know is they can rate them for safety. And as long in a type 1 leak, they're going to fix right away. Type 2 leak, they're going to fix relatively quickly. And a type 3, they're going to observe over time and eventually get around to fixing. It's a non-safety issue. But they weren't focused, most utilities, on environment. Now, we want them to continue to focus on safety. I certainly don't want anyone to get hurt. It's safety, 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 and environment. We wanted to give them the tools to make this possible and to make all the data public so that everyone can be part of the conversation. So that's what we did. One point, though, on terms of affecting the difference, again, going back to this fat tail, these are just 4 city curves of distribution. This is the cumulative percentage of leakage versus the rate. And this line is, these are the medium and high emissions. So if we look at the intercept, basically 45% of the emissions come from the high, in this case, from 14% of the leaks. Factor of 3 greater. 10% of the leaks in city green is 3, from a little over 30%, again, factor of 3 higher. Again, you can go through. You see there's almost always consistently a factor of 3. So if you can fix those more leaky spots, you get 3 times the amount of methane reduction than if you just looked at this lower end where the bulk of them are. They had never done that before. We're now working with utilities to implement this strategy so we can reduce methane emissions from their systems without even having to spend more money. Now, we want them to spend more money, but if they just implemented this on the already existing repairs, they'd see a big difference in the emissions rates. Bringing science. And then we launched this on a website that you can go to EDF. You can see this. And we launched with 3 cities, Boston, Indianapolis, and Staten Island. And at one point, someone sort of criticized, oh, you're trying to undermine the industry. So wait a minute, if we're trying to undermine the industry, we wouldn't have put Indianapolis in there. And Brian's done a lot of work there because that's a relatively, they had a, I believe it was 20 years ago, an explosion. Is that right, Brian? Do you remember about that? A little more. And so they made a commitment to replacing their pipes in Indianapolis. So they have a new infrastructure in Indianapolis. We only found in the streets, the areas we drove, 5 leaks. 1/200th the density of leaks in Indianapolis than in Boston. But in Boston, the pipes are old, they're cast iron largely. So what we want to do is get Boston to look like Indianapolis. But you're not going to do that instantly. First, you want to repair the really leaky spots using the data, and then working on accelerated replacement. To do that, we needed to get people concerned, but not fearful. So we did a lot of, I have a social psychologist on my staff. We did a lot of experimentation. How can we present this data to get people to understand what the message is? Almost all of my instincts on how we did it were wrong. All right? I'd readily admit it. So we should present it this way and that way. Well, we actually tested it, and it turned out almost all of our instincts were wrong in terms of what we should say. If you go on the website, you'll get one of these whirligigs, right? The thing's thinking. It's really not thinking. It's trying to get you to read. So we slowed it down to get people to read. We also wanted to know, how do you do the equivalents? How big and important are they? So this just gives you the Boston map. And then you see it says low, medium, and high. There's Indianapolis, just give you a sense. And then it says we used, so if you look up high, it says the same near-term climate impacts as driving a car more than 9,000 miles every day. And then the rate, more than 60,000 liters per day. Now, there aren't a lot of these high, but that would be the high end. And we originally thought, oh, we'll make it relevant to people. How many meals should you cook, right, that you could cook? Well, what does that do? That leads people to think about gas, home, explosions. All right, that wasn't our goal there. So, but this one gets people to think about the climate. We're used to thinking about the impacts on the environment of the cars we drive. Are they more or less efficient? So this worked Using home gas usage did not work. It got us to the wrong place. We are getting good response from public utility commissions that they're starting to talk about accelerated pipe replacement, deploying this methodology to fix the bigger leaks, and to start requiring posting of this data in the utilities under their jurisdictions. If that is really what happens, we've got a big win here. We developed the science to make it transparent, so rather than it being all off in the corner and not being aware, we get a public conversation about how to reduce methane emissions from the infrastructure we're all paying for and using. That allows us to get where we wanted to go. I'm going to stop with that and open it up to questions. And hopefully I gave you some sense of how we approach integration of the science into getting good policy and using that to ask questions and to take academic research and really push it to accelerate it so that we can do that in a sort of a new paradigm that I think is a really powerful tool to affecting change. Thanks very much. Questions, thoughts? Yeah.
So, in terms of getting the sort of average consumer, the general public, interested in this issue, has there been a discussion around, if the utilities in your town were more efficient and they weren't leaking, perhaps your utility bills would be lower?
Yeah, it's a little more complicated than that because you're actually being charged for lost and unaccounted for gas that's not directly proportional to the amount of gas actually lost. They have this, and Brian would probably be able to describe it better because you know the intricacies, and there's usually set by the PUC in the state as to how they calculate it. I think most of them are a fixed percentage, or it's there's a different methods, but it's not directly, and because your meters are not very accurate, there's a lot of uncertainty, and they're certainly not precise. There's a lot of slop there. And there have been proposals to reduce that and tie it to real emissions now that we can start to map them. We also had, I didn't go through, you have on here, we asked people if your city wasn't there, vote for a city you want us to come visit. And we've had numerous public utility commissions come to us and say, we want you to map our city. We've had some, we also get these votes from people, and we'll try and go out and get the ones that get high votes. We'll try and go out and map those cities. And again, we want then people like in Indianapolis to applaud and say, look, you guys made the right investment. There you don't need to do anything other than to say thank you. Thank you for making the investment. Because most of the time they don't know it, or they don't know that they made the investment in their city and they don't realize the other city didn't make the investment. Yeah?
So just in the accounting here, is this picture consistent with what the utility thinks its leak rate is?
Yes, it is reasonably consistent. In the case of these early cities, and I can show you a blow-up. So what we did do for the earliest cities, we worked with the utilities because we understood that we were still learning and we wanted to make sure that if there wasn't an agreement, we could explore why. So these early maps, we won't be going, not every utility will we work with or do it explicitly. These early ones we did very interactively. But we didn't change. I mean, none of this data were modified by the utilities, but we share it and say, did we miss something? Are we doing something are we missing something? And so the utilities saw these before they went up and didn't, we have done some direct co-mapping, and there are some false negatives for sure, because in order to do this, we were conservative. We thought it was better to miss something than to claim there's something happening that isn't. So we used very conservative algorithms, and we could increase or decrease the number of false negatives, things that appear, by driving more often. We drive everywhere twice right now to verify the peaks. Well, that's where we have these algorithms we developed, and we think they're pretty good. They're conservative, but they're fairly effective. And again, we're using bins as opposed to discrete measurements because we recognize there's large uncertainties. But it doesn't matter from a policy standpoint. You do not have to have the absolute. If you look at those curves I showed you, what we care about is getting those higher emitters fixed sooner. And that can be accomplished with this level. I am hoping this will all be, it's not yet published, I regret, but it will be soon submitted to be published. And then once it comes out, it's public. There's no intellectual property on this. And we hope that this will be version 1.0, and there'll be a version 2.0, and somebody smarter than we are can figure out a way to do this even better. But the idea is to open it all up, make this public, make this about a public ability to change and affect this kind of insight, because remember, all of this was, the utilities had these maps, but they were all behind the curtain. We've tried to pull the curtain open and say there's no reason to keep them behind the curtain. And not only that, it motivates people, right? They realize they have a problem. Well, let's do something about it. And it helps the utilities in the sense of if there is some increment that has to be put on their bill for increased pipe replacement, you're starting to understand why, rather than it just being about minimum cost, minimum cost. Well, it's not necessarily always the minimum. Obviously, you can't replace them all in 2 years because if you have a city like Boston, it's way too expensive and logistically impossible. Yeah.
Yeah, but that seems like it might be a selling point to the consumer if they realize that their rates are high because they're wasting all this gas.
The amounts are, it's marginally important. It's actually not, because remember, we're talking about a high leak rate for the entire United States would be, if it were 5%, that's a big number. And that's the whole supply chain. So, you know, and I'm looking at Brian because I have to be somewhat circumspect here in the numbers I use because we don't talk about numbers for the release. But the leakage here would not have a measurable impact on your lake, you know, because if there was 1% coming from a city, that's a lot. That's a lot of gas. And you know, that'd be 1%. You'd be losing 1%. You're already paying for it and you're lost and unaccounted for. So you might be able to see if they can reduce the leaks and change the way that they calculate lost and unaccounted for, you might be able to see a gain of a couple %. Because in fact, you'd lower that amount of lost and unaccounted for because you'd actually know how much it is. Other questions, reactions? Yeah. Well, some of them have actively gone involved in recommending it. So there are companies, Southwestern has been public about saying we should cap the amount of leakage that happens and that we'll work assiduously, and they believe publicly, I'm trying to remember the exact statements, I won't get it right so I won't try and say it, you know, that they can take that on and effectively reduce emissions. Some of the companies have appeared in a commitment, Statoil, which is international. I'm not going to remember which other ones were at the UN last week, publicly saying we need an international effort to reduce methane emissions, and they were committed to doing that. So some of the companies, and in Colorado, the bill that the governor, the rules that the governor worked on with EDF, there were 3 companies that partnered in developing those rules to reduce emissions from the gas fields. So again, I won't speak for the range of companies, but there are numerous companies who've gotten out and said, look, this is something we need to take care of. And I think that there's every reason to do it. I mean, we've got plenty of data to show you can reduce them a lot cost effectively. We might all disagree a little bit on how low we can bring them, but that's where the data that's coming out now will help us decide how low can we cost effectively do it. Given the distribution curves we've seen, the importance of the fat tail, I personally think we can reduce them significantly cost effectively. I think all the data points in that direction. I see Brian nodding his head as well. He's certainly thought about it. I don't know if you have a thought about that. Right, and we're seeing that across the supply chain. And we do have another study that we did that I didn't talk about here, where we've gone out recently and looked at in the production fields at these large emitters across the United States. We did 7 different plays, and we're summarizing all the data to look at the distribution curves and what percentage of different pieces of equipment have large leaks. Because the problem is, again, it's a sampling problem. You go out, and you have to understand that University of Texas study, which some people criticized as the sample size, they did 27 completions. Now that's 27 more than anyone else had done before, but some people criticized it and said, that's way too small a sample size. Well, that was also a $1.2 million study. You know, and sure, I'd love to have 100 more, but would the results significantly change? Is the way to figure out the fat tail by making it a sample of 500? No. Because we'd have, you know, the rare events, you sample those differently. So in the case of how we've been looking at the fields is we've been using fixed wing aircraft and helicopters with a couple of different methods across different plays to try and make those estimates. And again, we always make sure we have academics involved that are leading these efforts. Joe?
So focus here has been on the extant and very active production system from soup to nuts. And what about abandoned wells, and
Sure, great question. So abandoned wells is an issue for which we have essentially no data. There is a paper that I expect will be coming out relatively soon that addresses, not related to our study. I just happen to know about it because I was one of the reviewers, so I can't say any more than that. And we are in the middle we've commissioned some work that's going on and trying to come up with a first estimate on a more national scale. There's absolutely no national data, nor multiple. The one study that I expect will be coming out is just on a single, relatively narrow location. How important abandoned wells are is really important, and we don't know. There is some evidence in some locations that natural seeps, because remember, if we're areas that have high geologic concentrations, and particularly they think about the places they drilled first where it was close to the surface, some of those actually natural seeps, where gas seeps naturally just like oil. They're really confounding. So we are currently working in this urban area, and we've said that publicly with Southern California Gas, where they have some of those problems, where they have background thermogenic gas through natural processes, not because the system's leaking. So we're doing this drive-bys in that part of the country. We're working with the utility to see whether or not we can use these techniques in those cases where we have those complications, or we just get too muddled an answer that we can't really differentiate. And if so, then we'll know we have to avoid using these technologies in those places. So it's a really important question. We do have some data that we're collecting. I don't know, they're probably out today, actually, because we've got a couple groups out, because that's one of the holes that we hadn't filled. So, yeah.
How do you deal with public versus private property, and are you able to take information
from private property? Absolutely. So this is public property, so we're driving on streets, so we perfectly legal. There's no restriction. It's no different than you driving your car. There are restrictions, obviously. We do not go on private property to take samples. We do drive-bys, so to the degree, and some of the methods we used in the Barnett is using cars, and you drive by and look at the wind direction and infer from it, and it's some fairly complicated. Some of you are familiar with the physics involved in the modeling to do the air pollution modeling to figure that out. And then also we do flyovers. Now you have to be careful again. We made sure that when we did the most recent set of flyovers, we actually had our legal team reviewing all the legal applicable laws to make sure there's no restrictions. There are, for example, in Texas, it's illegal for you to take an unmanned vehicle and fly over it and make measurements. We did do some, as part of the Barnett, we did have some unmanned vehicles taking measurements, but we had property owner permission to work on their property to look at some of those to see whether you could do it effectively with those. So yeah, so that's one of the issues. So that's why when I mentioned like the production study, it was a coalition of the willing. So we had access to those sites, University of Texas. They, as I'm sure Brian could speak to how he did it, they didn't say, where do you want us to go? They made criteria, they gave it to the participating companies, and they did it right away, with short lead time, and then they would tell them, okay, we have these things happening in this place, and they'd say, okay, we're going to visit this site, and then they show up and do it. So there's no bias, there's no ability to be different, or at least minimal ability to be different, but it's on the companies that are cooperating sites. And then there is this issue, which we completely agree, is how well does that represent the others? That's why we do the flyovers, which incorporates everybody, and then try and explain the difference between them and try and understand, are we missing something? Are there some of the operators who are completely different that are just leaking all over the place and not representative, let's say, of the companies that participated? Yeah.
You mentioned that the leaks from the cities are relatively small contributors. So is it like the well?
Well, they could be a significant contributor, but I said we have to be careful. It's, I didn't say they were small contributors. Some cities it could be an important contributor. Right. But it's not 10%. I mean, I don't want to think about that. Like 10% of your gas is leaking out. That's not. That could theoretically happen in some place or some particular, but that's got to be very much aberrant.
So is it the wellheads though that are maybe potentially contributing more, or I mean, where's the largest?
Well, we will.
Sector
We will know that. I'll see if I can quickly go back to the figure I showed you. That's what we're trying to figure out. EPA has its estimates currently there. So these are based on EPA estimates, so they're percentages. But that's why we did all these studies. We are in the process, we are working with the National Energy Technology Laboratory, a DOE laboratory, who are working with us on integrating all the bottom-up studies into an integrated measure of the aggregate emissions based on the data that have been collected as part of these multiple studies. But that's not including them. We're going to take the top down and the bottom up, put it all together, look at it, where are the uncertainties and where is it likely the emissions. Now there was a study done by, it was a paper in the Proceedings of the National Academy of Science by a group out of Harvard, though with cooperation from a lot of NOAA folks and others across the country, and they integrated all of the tower measurements for the United States and came up with an estimate for total anthropogenic emissions, and it was 50% higher than the EPA. Which to my mind, some say, oh, it's much higher. To my mind, that's like, okay, it's higher, but it's not radically higher. So it was saying that EPA, not just from oil and gas, but also mainly from cows, from cattle, ruminants, to combine those together, EPA comes up with an annual estimate. Their best calculation based on direct measurements, air measurements, was that it was 50% higher than the estimate from EPA. So that's saying that, we know that these need to be revised. We're working on that data, but they're not grossly off. It's not 10 times higher or 1/10 as high. Individual pieces may be, and I showed you a case where it's true with well completions where it was tenfold difference.
So the leakage here, that 1.5%, is that of the total supply?
That's of the gas you pump out and how much of it will end up getting to the end user. Note here, we are not including emissions from the end user. I'm just gearing up, and actually Brian and I were talking earlier this afternoon about some ideas I have, and I'm just, hopefully, knock on wood, I'll have some funding in 2 weeks to begin to work on that piece of it. So in your house, I don't know how much leaks from my house or your house or from the power plant, from the use, not the supply chain. So I've been very careful in my language. I talked about the supply chain, not the full value chain. So at this point, there's almost no data on that end use, and EPA doesn't estimate that end use. So we're going to try and get our arms around that. And I would be pure speculation if I gave you any number now. I don't think there's anyone in the country, and again, Brian's an expert, so that's why I keep looking to it. I don't think there's anybody in the country who could give an answer to that right now on that end use. We just don't, we have so little data, it's very speculative. It would be taking a number and extrapolating well beyond what it could ever do. Yeah? So in terms of fracking, I can't tell you it's going to depend on the issue of whether fracking itself is not the issue, remember, because fracking is how you open the well as opposed to its impacts on whether it would affect abandoned wells. So fracking per se, there's no evidence that I'm aware of that it would affect leak rates to the atmosphere directly. It would come through a poor well casing. So if you had a well casing that didn't have integrity, but the actual below ground isn't going to seep up. I'm not aware of any data that shows that any gas, because you fracked it, is now getting to the surface. Now the question then of how does it influence abandoned wells, I'm not an expert in that. I'm not aware of any papers on that, but I would defer because it's just not something I know well. Well, you have different water. So the issues of water generally is also about the well casing. I'm not an expert on the water side of it, but for the most part, there's sufficient distance, and I'm not, again, looking at the literature, and I'm going to, again, look to Brian if he knows anything else. So the distance between where you're fracking in most cases, almost all cases, and where your surface water is very large. I'm not aware of any literature that says it gets up that way. What you do get into the water is if through the well casing, there's also issues of abandoned well casings. So abandoned wells, we do not have a good map of abandoned wells. Not all the wells have been plugged, I should say, not capped, plugged. And so one of the things, Rob Jackson, who's done a lot of this work on this water issue, who also works closely with us, so he's working on several projects with us, has documented these kinds of problems. And one of the challenges for methane is also, in a lot of the cases, there wasn't good pre-drilling data. So to what degree was that problem present prior? And to what degree does it come from coal bed methane? Does it come from? So I'm not saying that there aren't issues, but you have to sort out the sources of those issues. We are not, I should back up. We've done a lot of work on developing model regulations and getting states to adopt them to ensure integrity of well casings, because that matters a lot. You want to separate the well from the rest of the environment so that you're not leaking. So we've worked very intensively already starting a couple of years ago to develop these model regulations and then work with states to adopt those. And we are now starting to work with, but just barely beginning to work on characterizing water produced in wells and how to treat it, but we've not been working on methane contamination of water. There are other researchers who are doing it. As I said, Rob Jackson, who was at Duke, who's now at Stanford, has done a lot of work, and there's a group that he's been leading that's been working on that. Yeah.
One more question about making this information public. Have you had any contenders when it comes to making this information public, and how have you dealt with that?
I'm not sure what you mean by contenders.
What kind of arguments have you had against making it?
All of it's public. The only thing we do is we mask the data for companies, which is fair enough, so that when you can't figure out which well is by which company. So if they're doing this voluntarily, they shouldn't be subjected to added potential regulations. So you can't say, you'll have all the data there, but you don't know if it's company A, B, or C. And then when we make this, when we do the mapping, we make all the verified peaks public. So that's, anybody can get that. You can go on it and see where is this data. That's all, we'll share that. And we'll share the data that underlies that and how we developed it with any researcher. Because it gets pretty complicated really quickly. So we said, the average person wouldn't be able to deal with that data. So we say, if you're a researcher and you have a legitimate question, great, here's the data. And then if you go back to what we call the unprocessed data, sort of the stuff straight out of the machine, you need to have a really good reason, because it takes a bunch of quality control just to make sure you don't have garbage in there. Because when we started driving, a lot of that data we had to throw out because we learned how to drive properly, when was it too wet, when was the wrong conditions, and so we threw a lot of data out. And so if you don't understand what to look for, you could have bad data and you could accept it. And so we clean that up, again, in no biased way, just what's a good number, and then that's what we process. And so we don't want people using that raw data and not understanding those restrictions. So we'll share everything. In terms of the studies, there'll be, I assume, a website here at WSU. When that paper gets published that day, you'll be able to go online and get all the data that's underlying that. It won't say, I assume, it will be masked for the utility, so you won't know if it's utility A, B, or C, but it'll be there, and you can look at it and say, well, I think you could analyze it another way. And we have had one case where somebody said, I think it should be analyzed a different way. Great, analyze it that way. That's your prerogative. Now, we might not agree, and we may have a scientific debate on whether that's an appropriate way, but we want to make sure that it's totally transparent, and you don't have to take it, and anyone can calculate it however they want. Yeah?
Unrelated to methane, I'm curious how EDF prioritizes its projects, fundraise for it. How does that happen?
Oh, that's a great question. I'm not sure I can give you a good answer. We make a value judgment on where we think where the most important environmental problems are and where we think we are in the best position to make a difference. So on this methane, it wasn't something we worked on 4 years ago. We started working on it, it looks back about 3 years ago, I think, and it came from the work that I did with my team on trying to think through how important this might be. And I convinced internally, we did a lot of work with academics and others, that in fact that was true, that this could make a difference and that this could have an effect on the climate, and this was an important, for lack of better terms, lever that we could push down in the policy arena to make a difference in a way relative to the other things we could possibly be working on. And so we committed heavily, more so, I mean, we're more involved in this issue than any group, period, not even environmental. I mean, we have more researchers working on this through our program than anybody, period, the government, anyone. Now, they're not all EDF employees. They're people like the folks here at WSU who are doing that work in part with our funding, and I'm sure they have other funding and sort of doing that work to do that. But that's how we sort of decide, and we decided that working on these short-lived forcers, short-lived climate pollutants could make a difference to the climate. We care a lot about the climate. We think climate change is a big issue for the environment, and that reducing those methane emissions. We also have a big commitment on clean energy and renewables, because we don't think that doing natural gas is the solution. We want to reduce methane and we want to reduce fossil fuels absolutely as quickly as possible. We got to get rid of coal first That's going to have the biggest impact on climate. We're very strong supporters of the 111D process of reducing emissions from power plants. And we got to reduce total fossil fuel use absolutely as fast as we can. So we're not just working on methane, we're working on clean energy with the states. How do you integrate renewables into the power grid? How do you get the rules right for doing that? How do you get the incentives right for getting as much renewable as possible? We have a big team working on that. And we think with that combination approach, again, sort of go back to the and proposition, we got to do both. We got to get these short-lived forcers down, we got to get the CO2 down, we got to push as hard as we can on both at the same time. Joe? Yeah. Yeah.
Are there some states that are trying to make it harder, like sell renewable energy back onto the grid?
I'm not an expert. I'm going to have to deflect. I don't, because we do have folks who could give you the answer right off the top of their heads because they work on it. It's too far from what I'm doing, and I'm going to beg off that one. Sorry. Joe?
Arizona, for one, had some very attractive things for homeowners to sell back to the grid, but with state-level politics, change in the commissioners, the utility commissioners, this stuff goes away or comes back.
But
I think it sways with political winds, but I think there was some study or frontline story about Kansas or some Midwestern state that had great incentives, and then the administration kind of changed over and then they just tanked it all.
But remember, it's integrating. So again, I won't get into the details because I feel not well enough informed, but the key is how all this integrates. So the anecdotal study, but I think makes the point, is in New Jersey, and I don't know to what degree in New York, people had PV on their houses when Sandy hit, and they didn't have any power because the whole grid went down, and they weren't set up to allow them to run independent of the grid. And there are also issues about grid reliability. How do you get all of the incentives right so that you can integrate all this effectively and maximize the renewables and the impact that they can have? And again, I'm not an expert, but we have people who that's all they do full time. How do you get the rules right to ensure that you get both maximum renewables and maximum reliability into the system? And you can't do that by just putting renewables on the existing infrastructure and rule system. You have to, there are changes that are needed, and as you see in Europe as well. So it's how do you do that? So I just want to make the point, which I was stressing, is we're working on natural gas and we're doing that other side because both have to happen. It's not, I'm working more on this, so I talk more about this, but I got to have someone here standing up and spending the whole time talking about how you do that clean energy integration and the renewables, because we're going to have to do both of them. Yeah.
So one thing that seems kind of nice about is it feels like this is a problem.
Exactly.
And it seems like I'm kind of curious as to why you think the natural gas industry is so damn receptive.
Well, that's an overgeneralization.
Okay, fair enough, but they certainly do seem more receptive than I imagined say, the coal plant would be, or the coal industry would be.
Well, I think some of it had to do with, and again, I'm getting a little outside of my science, so I'm going to try and tread carefully here, but the social license to operate was threatened by a lot of pushback, a lot of legitimate pushback that local communities had about poor practices, pollution, and so as they face that threat, that becomes very real in places. And I won't speak for their motivation, but it's certainly, I don't think, I'm saying anything that wouldn't be obvious to folks, that there's a lot of places where people were saying, look, we don't want this. And again, for a lot of good reasons. They were not well controlled, or nobody was making sure they did it right. And we're always saying, you shouldn't be doing this unless you get the rules right, and then we want to do it only to the limited degree we need till we can transition to cleaner fuels. So I think that's part of it. And then it's like anything. There's a population of companies and people in companies. Some of them got it, and some haven't. And again, I won't make commentary on those individuals. But so we started out. I mean, you have to understand when we started this. Gosh, I'm so bad with time. I'm looking at Brian again. Is it maybe 2 years ago or so? So when we first, and the study that Brian leads is a little bit later, just because we had to phase it. We just couldn't chew all of these off at once. So probably the very first conversations we had were not quite 3 years ago. you know, people were, this was a whole new idea, not just about doing natural gas, but this partnership led by an NGO, getting these academics led, working with these companies. It wasn't like people would say, oh yeah, we did that last time, it really worked. Said, we haven't done this before. So there was a hesitance, but as we explained and described how we saw this playing out, what the rules of the road were, so the companies get to comment to Brian. I mean, they got to sit there and say, I think you this, what, or that. At the end of the day, it's his paper. He got to write the paper. And I think people got comfortable with that he was going to listen, as were the other PIs. They were going to take it serious. They knew things. And one of the things that we found, I've found in one of the groups that I've sat with, is, you know, I had a company point out in a case where one of the academics were missing a whole bunch of leakage because they had not measured something. And, you know, it was pretty bold because it was not going to make their company, their segment, I'm going to keep it pretty diffuse, I apologize, but, you know, look good in that regard. They said, look, bad data is going to undermine us anyway. And, you know, we want to get the best data we can to define the problem. Well, they get a head start in coming up with the answer of how they're going to solve it because they know it's there. So that's what they have, and they're already working on the solution. But they pointed it out. We might have totally missed it because the academics didn't understand. There were some nuances they didn't get because they didn't realize something was happening, and so they weren't looking. Once they looked, they went, oh, this is a big deal. You're right. But now they're already, by the time we launch that paper, they'll have the answer. This is what we're doing as a company to ensure that doesn't happen going forward. And so, and many of the companies have seen that. They've seen it as an opportunity for them to learn, for them to understand what was going on. Again, those are the willing. I'm sure there are others out there who wouldn't view it that way, but they're not working with us.
Well, I was actually kind of wondering, I mean, it seems like there is an incentive. I know you said, you know, loss and all that is usually tacked on to the consumer.
Well, the local distribution.
Yeah. So, but I'm thinking production, though. Production, they're looking at this.
Sure.
It seems like a great selling point to say, I can keep your inventory from actually having some loss. I can actually help your loss prevention in this regard. So there is at least some offset to the opportunity cost I'm actually going to impose upon you. So I can kind of see that. I'm wondering, though, and this is where my question's heading, because it does seem like, I know, okay, so maybe I overstated it. It still seems like the natural gas side seems to be cooperating better than other sectors, let's say.
I don't know the right answer. I don't study enough sectors to know what the distribution of the community is relative to other communities.
Okay, fair enough. Assume I'm right.
You're right. Okay, we'll assume you're right.
But I guess I was wondering about the abandoned well thing, though.
There's no incentives there, and that's why we've got to raise the issue.
Wondering.
Absolutely. And so we're just, again, what we're trying to do is, ultimately, we're trying to understand the sources of methane from human-caused activity that we could do something about. And so we are involved in looking across the spectrum. We started with the places that made sense up front, and we've been working our way down the list, and abandoned wells was clearly one of them. It wasn't something that there was any data with. As we went through and we realized, gee, there's a big, you know, potential source. Maybe that's one of the reasons the top-down and the bottom-up don't add up, because none of the bottom-up include abandoned wells. We realized we had to at least start getting some data, and so that's where we're spending pure EDF money. We've hired a contractor who's out there making measurements, you know, they came up with a study design. We vetted it with some scientists and said, okay, and go out and get us some data, because we can't go public with the big integration with at least some guesstimate on how big. It's not going to be a good number, but at least a first approximation. We looked at enough wells to say, yeah, that could be a big deal, and somebody, whether it's us or not, our goal in this is not to keep doing the science. Our goal is to see this and get others, and the government is stepping up and doing more science, and hopefully they'll be taking it over. So if it turns out that abandoned wells are a really big deal or even a modest deal, I would hope that there would be a pretty quick response on the part of government, and that we don't have to fund another big study, but we have to get those answers, absolutely. But we're going to do the pilot. We're doing it literally. I'm sure there could well be at this hour folks right out right now in the field making those measurements. Joe? Or, yeah.
So this model, last time you were here, you talked about how focused EDF was in, I believe, the general discussions of climate change science and looking at prospective actions, about getting the process agreed to by parties, independent of any assumptions of where you come out on what you're going to do eventually. So who, Jeff, has demonstrated applied to natural gas system, who's going to pick it up abroad and try it?
So we have,
Countries, what economies or groups of countries?
so I can't give you the specifics, but I can say that the head of Statoil, whose name I've forgotten, I apologize, stood up in the UN last week and said they're in. And the head, I'm not going to get it exactly right, but I believe he's the head of the largest natural gas oil company in the world from Saudi Arabia, Saudi Aramco, after said, I'm in, when he gave his speech. So right now we're starting to work heavily internationally, and there's a set of companies that are saying they want in. And one of the things that I'm very interested in working on is how do we sense methane in environments where maybe I can't send 4 planes up, or I can't, Brian or the equivalent of Brian can't go drive his cars and bring all his equipment and go work on the middle of the street. And so we're thinking a lot about that and working with, again, having a set of conversations with people both in the academic world and the private sector on how could we do that. There's some satellites that are getting launched. We're looking at all of that. And so I don't know the answer, but absolutely, we got to, doing in the U.S. is the starting place. Now the advantage we have for the U.S. is that because we could get these accesses and we could develop our techniques, we can also then, if we do use remote sensing techniques more and all of that, we can look back to what we've done in the United States where we say we think we pretty well know. In the place right now we know the best is the Barnett in Texas, because we've done all this work. I mean, we've spent more money looking at methane emissions than in Barnett than any place on earth probably right now. And so we have this good, and so we would do those techniques there and say, well, what are, it's a way of calibrating and validating approaches. But we've got to solve the problem globally. It's not a local problem for sure. But doesn't mean we don't have to do our bit here in the U.S. And the potential advantage is a lot of the international oil and gas companies are vertically integrated. So here, we go from one sector to the next, and we're working with different companies. The gas one company doesn't own it from production all the way to sales. They hand it off. Somebody sells it to the next person. Some people you pay to carry it. Some people own it. I mean, it's complicated hiring. So we have different companies. We have a total of 90 partners. That's academics and corporate partners. And that's just, WSU counts as one, though there are multiple people who worked on the project from WSU. And so then when we look at individuals, it's a much bigger number. So absolutely, we're going international. We've already started. So next time I'm here, I can tell you about what's going on internationally, I hope. Yeah.